Thank you. I'll begin with a word of prayer. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. I just pray that you just bless this class today. Help us to, again, glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. Okay, so I'll talk to you guys about power series. Some more. And, we have covered different bits and pieces of chapter 12, obviously. I think I've stated Taylor's theorem for you. I've shown you some Taylor polynomials. Now I'm going to just take a little bit of class time to discuss basically section 12.8 with you. So 12.8, where to start now? Okay. That was fun. Is on the basically the domain of power series, all right? And I've alluded to this material a couple times, but I just want to sort of state it and prove a couple things for you. Shouldn't be too difficult. And it's also important for us to kind of know our boundaries, so to speak. So this is section 12.8 on theory of power series. Basically. And so the fundamental theorem that kind of guides a lot of our thinking is this theorem. If f of x is equal to the sum, all right, n equals 0 to infinity of a sub n, x minus x naught to the power n, all right? In other words, we have a power series that's centered at x naught with coefficients a sub n, all right? Then the domain of f is a connected set. Connected set, what's that mean? That means if you think about the set on the number line, you can draw it without lifting your pen, if you like. Another way of saying it is it can't be written as the union of two disjoint open sets. Anyway, basically here are the possibilities. More specifically, that was supposed to be specific. I think I'm missing a C. Specifically, 3 cases. I'll start out with the most boring case. 1, the domain of f is just equal to the set containing x naught. So it could be that this series has a domain which is just one point. It's a very stupid function. But that's possible. This formula might only make sense at the center. That's possible. Another thing, case 2, is that the domain of f looks like, well, includes x naught minus r to x naught plus r, and some collection of the set x naught plus r, well, excuse me, x naught minus r, x naught plus r. Let's see, that's I don't know. I have yet to figure out a really slick way of saying this. Let me just tell you that there's 4 cases here. It's an open set, so it really is just this. That's one possibility. The other possibility is that the bottom endpoint's not included, but the top endpoint is included. Another possibility, the lower endpoint is included, but the upper endpoint is not included. And finally, another case possible is you can have both endpoints included. All 4 of these cases, really subcases of case 2, have the same so-called open interval of convergence. This is the open interval of convergence, and it's shared by all 4 of these actual intervals of convergence. So the interval of convergence is what it sounds like. It's the interval on which the power series converges. This makes sense because power series only converge on intervals. That's essentially what this theorem says. Power series converge on an interval, some kind of interval. It could be a stupid interval. Maybe this is sort of a degenerate interval, right? One of these half open, half closed, or right? And then what's the third case? Yep, the domain of f is equal to the whole real line. So a little bit of terminology while we're at it. We define the interval of convergence to be, like I said, the domain of the power series, the given power series. The radius of convergence, well, let's define that. So this guy, radius of convergence, 0. This one, the radius of convergence is r. Okay. Sorry. Let me just say that this is the radius of convergence. Here, whatever number that r is. And down here we have the radius of convergence is infinity. So them's your choices. 0, some finite positive number, or infinity. Those are the possible radiuses. Okay? Yeah?
So it's not possible to like from 0 to infinity?
No, we cannot have a power series that has domain 0 to infinity. That can't happen. So when I said it was a connected set, it's not just a connected set, it's a specific kind of connected set. In differential equations, we study something called the Frobenius method. The Frobenius method has solution sets that are like rays that go from the singular point out to infinity, but that's a different thing. Anyway, so them's your choices. Let me give you examples. How about this? If we have f of x, here's my favorite example, n factorial times x to the n equals 0 to infinity. So its center is at 0. And how do you decide where this converges or diverges? Let me suggest this. This is my a sub n, right? So I could do the ratio test here, right? Are these positive terms? Well, find. I guess I can't. Oh, but we can check for absolute convergence, can't we? Oh, fine. I guess I've got more work to do. Let me not use the ratio test. Let me use the. How about the nth term test? If this is a sub n, what does it go to? A sub n factorial x to the n. This clearly does not go to 0 unless what? Right, unless x is equal to 0. I would point out if x is less than 1, there's an ambiguity there, all right? So, but, by the way, if x is equal to a half or something like that, for example, then we have a sub n is, n factorial over 2 to the n. And that also does not go to 0. Again, that would take some work. I'm summarizing. You could write a page of work to prove it carefully. Half page. There's cases to consider. But in the end, n factorial will beat the exponential, whatever it is, right? Because x is fixed, and you're taking the limit as n goes to infinity. So x to the n is at most exponential. Whereas n factorial is, well, n factorial, and we know n factorial will beat down the x to the n. Example 2, we could look at something like, I don't know, how about f of x equal to the sum n equals 0 to infinity. Let's say I'll make it interesting for us. 2x minus 1 to the n. This is not a power series, right? How can I make this a power series? I guess I should start with a power series for the sake of this example. I'm sorry, guys. Let me behave. What would this be? What should I start with? This is the man behind the curtain. Here's what I should start us with, maybe. How about 2 to the n times x minus 1/2 to the n, right? There's an honest to goodness power series. It makes sense to talk about that as it relates to this theorem. I guess this is technically out of bounds. That's not a power series, if I may be picky. That over there is, its center is 1/2, and its coefficient is 2 to the n. Right? So here, what's the... Well, the thing is, that's a geometric series, right? So you can recognize this as being, well, I mean, I kind of gave it away over here that it was geometric. This is really equal to, how's it go? I mean, this is a power series, right? But if I look at this, this is a geometric series. In the sense that I have what? This is, you could think of this as a r to the n with r equal to what? This stuff here, right? This is r. So I know that that will converge when? When does a geometric series converge? When you be r, the magnitude of r to be less than 1, which is tantamount to requiring that the absolute value of 2x minus 1 be less than 1, which is what? That's minus 1 less than 2x minus 1 less than 1, aka add 1, you get 0, less than 2x less than 2, also known as 0 less than x less than 1. Right? So in other words, the domain of f here was what? It was 0 to 1. What's the radius of convergence? One-half, right. So this is the IOC. It's also the open IOC, and the radius of convergence here is 1/2. If you start thinking about why that is, it makes a lot of sense. If you think about this up here, right? What happens when I get to 0? Here. Think about putting 0 in here. What do you get? Minus 1 over 2 to the n. So this gives us a minus 1 to the n, right? That does not converge, right? It fails by the nth term test. If you think about plugging in 1 into here, this becomes 1 over 2 to the n. That cancels the 2 to the n, and you've just got the sum n equals 0 to infinity of 1. Of course that diverges, right? So it's easy to check the endpoints here, 0 and 1, and see that, in fact, yes, our power series diverges at those points. Yep.
Domain of that includes that interval. It can include a bigger one or just exactly.
I'm sorry?
Domain of it is exactly x from x0 minus r to the x0 plus r.
It can be any of these 4 possibilities for different examples.
I mean, like just exactly
This one, the domain is exactly the open interval.
I mean, like maybe it's not like from x0 to both sides.
Well, this one includes neither side. It could include just one side or the other. For example, last time we found the series.
I mean, like the domain includes that or exactly?
The domain is exactly one of these four possibilities.
It's not bigger.
Yeah. It's either the whole real line, one of these finite cases, or just the single point. Last time we worked out the power series of log of 1 plus x, remember? And we found that that was equal to the sum, if I recall correctly, n equals 0 to infinity minus 1 to the n plus 1 over n plus 1. Was it x to the n plus 1? Am I right? I think I worked that out. Now, I didn't actually prove, if you want me to be picky, I have not proved that this series matches this function at the end point. If you want to get picky, I haven't done that.
No, it's just that, like, I mean, that includes me that can include another one, perhaps.
Can you make it bigger?
Yeah, can you make it bigger?
No.
Because the domain of the natural log is bigger, right?
You're thinking about a separate issue. So, yes, the domain of the log is larger, right? This, indeed, I mean, Nathan is right. I mean, the domain of the log includes more than the interval of convergence of the series. This equality is a limited time offer. This equality is only good from, like, I want to say 0 to 2. Wait a minute, what is it? I forgot now. Is this right, guys? I need to convert.
Yes, that's right.
Okay. So, to be more specific, I should call this thing g of x and say, okay, so what's the domain of g? All right, what's the domain of g? So,
It's supposed to be negative 1 to the n. Not plus 1.
this is negative 1 to the n? Okay, thank you. That's important. That's actually really important to this discussion. So, excuse me, example 2 tilde. So how do you figure, I mean, I have been fortunate in these ones to either basically guess or to argue from geometric series what the interval of convergence is, all right? But we can also use, there's a little bit more to this theorem. There's a little bit more. Here's a little bit more. Moreover, the power series is absolutely convergent. All right? On its open IOC. Now, the open interval of convergence is either the open interval, x naught plus or minus the radius, or it's the whole real line. There are only two possible open intervals of convergence. This is something, I mean, that's an anomaly, all right, but excuse me. In case one, the open interval of convergence is empty, so it's kind of a moot point, but all right. So what that means is to find the open interval of convergence, I can test for absolute convergence. How do we test for absolute convergence of a series? What's the tool for the job? You take the absolute value of the series, right? Which means then we're looking at a series with positive terms, for which our most favorite convergence tests exist. May I recommend to you guys the ratio test? So we can use the ratio test on this. So if this is, a sub n, we can look at the absolute value of a sub n plus 1 divided by the absolute value of a sub n. And what's that going to be? Excuse me, n over n plus 1 times the absolute value of, well, x to the n plus 1 divided by x to the n. All right. We assume x is not equal to 0. We already know x equal to 0 is in there. X equal to 0 is automatically in the interval of convergence. We're not worried about that point, right? I have to say that because I'm dividing by x here, right? So can you simplify that? We got what? We got n over n plus 1 times the absolute value of x. So what did the ratio test tell us? Do you guys remember? Right, so we need to calculate the limit. And what happens if the limit, so we need to calculate the limit n goes to infinity of the absolute value of n plus 1 over the absolute value of a sub n. Notice that the absolute value of x is just a constant, so we pull it out. And we're left with the limit as n goes to infinity of n over n plus 1, right? You see what I did there? I'm saying that this has no n dependence, so it pulls out of the limit. It's just a number, whatever it is, who cares? Pulls out, positive. And this goes to what? Oh, very good. This one goes to 1, so the whole thing goes to, you say x, but I would caution you to say absolute value of x, okay? Right, because that limit's 1. And so, in order for the ratio test, what's the ratio test? The ratio test says if this limit is less than 1, it converges. If that limit's greater than 1, it diverges. So a condition that we need, hence, you know, g of x is a real number when the absolute value of x is less than 1 by ratio test. Right? By the ratio test, that series converges precisely when the absolute value of x is less than 1. So the open interval of convergence, right, therefore the open IOC is equal to minus 1 to 1. It remains to check endpoints. So the ratio test will tell us what the open interval of convergence is, and by guilt by association, essentially, that will tell us what the radius of convergence is, because you guys can tell me what the radius of convergence is now, right? What is it? It's 1, right? That interval has length 2, so half of that is 1. The radius is 1. What's the center? The center of this power series is 0, right? It's a Maclaurin series. How do we check endpoints? Plug them in. What are the endpoints? How about minus 1? G of minus 1 would be what? Uh-oh. Uh-oh, what do we got? This is a what? It diverges, right? This is the p equals 1 series. So we have to throw out that endpoint. The left endpoint is not included. Agree? Because the function doesn't make sense there. Its definition diverges. On the other hand, if we look at g of 1, right, what does that give us? So this converges by the alternating series test.
Isn't it negative 1 to the, would it be negative 1 to the n times negative 1 plus 1?
If I, well, was that? Oh, that was a minus. This is right. Okay, so fixing that. Let me fix it. Right. That puts a minus here, and it There? Okay. Thank you. But the outcome is still the same. We do not pick up the left endpoint of the open interval of convergence as a point of convergence. But on the other hand, one does work. So in total, we find the interval of convergence here is -1 to 1 included. Does that, I don't know if that, I mean, your question, I think, is more about analytic continuation.
No, it's about outside of that interval, it always diverges,
Right, yes. Yes, these are the interval of convergence. It either converges or diverges. Outside of here, game over. Yeah. That's actually a good question. So anyway, what's an example of something, how about something that converges everywhere? Should give you an example of that. Example 3. How about h of x equal to, I don't know, let's do e to the x. All right, so make it a little bit more exciting. Make it e to the 2x.
What? I'm sorry, I missed what the AST stands for.
Alternating series test. It's okay.
Thank you.
So here, this, well, let me see here. I don't really want to say e to the 2x. That's not what I mean. I'm supposed to look at a power series here, right? That's our discussion. So n equals 0 to infinity. 2 to the n, x to the n over n factorial. I happen to know by substitution that's the power series for e to the 2x. All right, but forget about that for a moment. What's the interval of convergence of this? So all you do is you apply the ratio test, a sub n plus 1, to the absolute value of the thing, all right? Now I'm going to do this again, but after you do this about 3 or 4 times, you should start to notice you don't really need to do the calculation with the x's. What's going to happen? Well, let's sort it out and see what happens, but 2 to the n plus 1, x to the n plus 1 over n plus 1 factorial times n factorial divided by 2 to the n times x to the n, absolute value of all this stuff. So what happens here is we've got an absolute value of x that simplifies out, right? And then we've got the absolute value of, looks like 2 to the n plus 1, which I can write as 2 to the n times 2, right? And then I got n factorial. Downstairs, I've got n plus 1 times n factorial, right? Because we can simplify n plus 1 factorial to n plus 1 times n factorial like we did before. And then I got my 2 to the n, right? Of course, some of these things cancel, right? What am I left with here? Like the 2 to the n's cancel, right? And the n factorials, those are gone. What are we left with? We're left with 2 times the absolute value of x divided by n plus 1. And again, we're looking at x not equal to 0 because we already know that 0 is in the interval of convergence, whatever case we're in. The center's always there by the theorem. What happens to this as n goes to infinity? Yeah, this goes to 0 as n goes to infinity, independent of x. X is fixed in this limit, right? It doesn't matter if it's Donald Trump's net worth, the national debt, your student loans after you're done here, whatever. I mean, whatever that number is, it's a fixed number, and as n goes to infinity, it beats it downstairs, right? So that goes to 0. So the ratio test always is positive, converges, which means that that series converges for all x. Does that make sense? So thus, the domain of this function is equal to minus infinity to infinity by ratio test. Remember when I said earlier, I don't do too many examples of ratio test earlier because we just keep doing ratio test over and over and over again here while we get to power series. It's our main tool to figure out the interval of convergence for a given power series. If you don't know its origin. I mean, if you know the origin of the power series, then, we can get intervals of convergence through other methods, right? I didn't need to use the ratio test to tell you that the interval of convergence here was 0 to 1, because this was geometric series, right? So geometric series comes with many rights and privileges entitled thereunto. I mean, it's got super cool convergence formula. It tells you when it converges, when it diverges. No need to check endpoints. I mean, man, geometric series are where it's at. Make sure you own that result. Any questions? All right. I would like to prove something. Yes, I think I have time. And the result I would like to prove for you is the following. Theorem. If f of x is equal to the sum of a sub n times x minus x naught to the n equals 0 to infinity, then g of x equal to f prime of x, which in other words, I mean this sum n equals 1 to infinity of a sum, good grief, n a sub n x minus x naught to the n minus 1 has same open interval of convergence as f of x. In other words, the radius of convergence is the same for the function and its derivative. All right? So here's the proof. Let's see here. If we look at g of x equal to the sum bn x minus x naught to the n minus 1, I guess I should say bn minus 1, n equals 1. I mean, so that's the, if we look at the series for g, we could look at it like that, where what? Where b sub n minus 1 is equal to what? It's equal to n times a sub n. Right, so the coefficients of the derivative series are related to the coefficients of the original series in this way. Right? So if we look at the ratio test for x naught equal to x naught, if we look at, b sub n divided by b sub n minus 1, right, considering the ratio test, what do we get? If this is b sub n, what's b? If this b sub n is my words are difficult. What is b sub n? n plus 1, right? A sub n plus 1, right? Very good. So check it out. So b sub n is n plus 1 times a sub n plus 1. And, oh, I'm sorry, I'm just a second. I should look at b sub n times what? Times x minus x naught to the what? N over x minus x naught to the n minus 1 in my current way of thinking. All right, so simplifies to absolute value of x minus x naught out front, and then we've got absolute value of the b sub n over b sub n minus 1. All right, now I will go ahead and translate that to the a sub n's. What do we got? We've got absolute value of x minus x naught times n plus 1 a sub n plus 1 divided by n times a n. Now, think about this. What's this go to? This goes to the absolute value of x minus x naught times the limit as n goes to infinity of a sub n plus 1 over a sub n, absolute value, I suppose. Right? Because what? I mean, the other term here, n plus 1 over n, what happens to the n plus 1 over n? That goes to 1 as n goes to infinity, right? So then, this comment I'm making makes sense in all the relevant cases, all right? So like, let's see here, let's trace through some different things. What if the radius of convergence is infinity for the function? What does that say about this? If the radius of convergence is infinity for the function, that means that the limit of a sub n plus 1 over a sub n times x minus x naught is equal to what? It's equal to 0. I mean, long story short, if you run the ratio test on f of x, right, you get this. This is what the ratio test for f of x gives you. So the convergence or divergence of this is precisely linked to the convergence or divergence of that. So the ratio test works for the derivative series exactly when it works for the original series. Again, just to trace out an example, a different case. What if, suppose that, oh goodness, sorry, let me stop talking. Any questions? Let me stop talking. For another example, if the this is very silly, but if f of x just converged at x naught, right, then that means that that this limit only, that this always diverges, basically. It means it's always greater than 1, or possibly infinity. And only at x equals to x naught does the convergence work out. Anyway, the point is they share the same interval of convergence. So. All right, so one last example, you guys. I'll let you get your quiz. Hypothetical. Suppose you're given that 4 and minus 2 are elements of the domain of f of x, and f of x is equal to the sum n equals 0 to infinity of, stuff I don't know, x of n times x minus 1 to the power n. A, find maximal IOC. B, find minimal IOC. In other words, find the largest and smallest intervals of convergence that are consistent with having 4 and minus 2 in the domain of this function that's defined by this power series, all right? So let's see here, just to draw a picture. minus 2 we're stuck with, 4 we're stuck with. All right. Where's the center of this thing? 1, let's see, 0. So it's right here somewhere. Oh, don't worry, that's not a quiz question. Don't worry. I mean, it should be, if I was more with it. This stupid cough has made me too nice to you guys this week. Let's see here. You're like, you're being nice? Sorry. I'm trying. So guys, I'll start us out. The maximal IOC. I want to be as greedy as possible. Oh, there's just not enough information. Sorry, this is stupid. Well, is that, I like it more when I throw in a point of divergence. This is too boring. Let me say, let's say minus 2 is in the domain, but let's say that 4 is not in the domain. That's more fun. We could still make sense of the previous question. I just think this one's more interesting. So points not in the domain, I like to draw as like little X's, because like if you get there, you're dead. Okay, so basically that 4 is how far from 1? 3 units, right? So you can't get past that. So the maximal interval of convergence would look like this. You go all the way out to where it gets to here. This is not included, right? And then symmetric, this is r equals to 3, right? So minus 3 takes me where? To the 2, huh? Oh man, I have the worst luck. Oh, come on. Well, fine. This is not as interesting in this example as I was hoping for. And so minus 2 is included. I have to do that. Oh man, well that's... Fine. I'll have to do more of these some other day. So there's the maximal interval of convergence. You can't do better than that. And it's also the minimal interval. Does it ever happen? Oh, come on. It isn't. What's the minimal one?
No, because negative 0.5 would be the center. The interval -2 to 1. You just have that.
What do you mean? 1 is the center. I'm stuck with it.
Why? Oh.
I can't move the center. You can ask another problem where the center is movable. There's lots of different twists on this problem. Tell you what, we'll try to, I'm sorry. This is a quirk of this stupid example. It's got the same stupid minimal and maximal intervals of convergence. Oh, you don't understand how unlucky this is. All right, quiz. Yes, quiz. Quiz 9. Or A, I don't know if you guys want to say, if A equals 0 means something more to you, you could say A equals to 0, whatever. Question number 1. Question number 2. Find first 3 terms in expansion of f of x equal to, let's say, x squared plus x e to the minus x about 0. There you go. Sorry, I didn't get any geometric series tricks into this, but rest assured they will appear on the test. So.